Welcome back to another statics video. In this video we are looking at one more truss analysis example. This is problem 5.7 from the textbook. So this problem uses metric units. We have loads in kilonewtons being applied to this truss, and the truss dimensions are given in meters. So the first thing we want to do whenever we start any truss analysis problem is to find any missing geometry, and the specific geometry we're going to be interested in for this truss analysis is to find what this angle is. This angle is going to be the same as this one because they are the same shape, 6 meters wide, 8 meters tall. These two rectangles with the diagonal braces are essentially stacked on top of each other, same size. So if we find one, we find them both. So we can start with that. Theta is going to be equal to the inverse tangent of the opposite over adjacent sides. So that's going to be 8/6. And let's see what that's equal to. That gives us 53.13 degrees. So that's the first step in the process. The second step will be to find the reaction forces. So we have a simply supported truss, meaning that it is supported by a pin and roller connection. The pin connection has 2 reaction forces. The roller has 1 reaction force. We can start by finding the reaction force at F by summing the moments about point E. So if we sum the moments about point E, they will equal 0. So I'm going to start with this 20 kilonewton load. It has a moment arm distance from E. Remember, the distance has to be perpendicular to the line of action of the vector. And since this is a horizontal vector, that means the moment arm distance is the vertical distance of 8 meters. This force moving horizontally is going to go around point E in a clockwise direction, and our sign convention tells us that a clockwise moment is negative. Next, we have this 10 kilonewton force. Its moment arm distance is 16. And it's causing another negative clockwise rotation about point E. Now the 100 kilonewton force up here is being applied at joint A, this vertical force. It's going to pass straight down and go right through joint E. So therefore it has no moment arm distance and therefore causes no moment. However, the 100 kilonewton force at joint B is going to cause a moment. And its moment arm distance, since it is a vertical force, its moment arm distance is horizontal, which is 6 meters. And that is also going to come down and around joint E, causing a clockwise or negative rotation. So far we have 3 negative moments caused by these applied forces. They are going to be resisted by the reaction at F in the y direction. Its moment arm distance is going to be 6 meters. And it is going to be going in the opposite counterclockwise direction. So it's a positive moment. So the sum of these 4 moments should equal 0. We have one unknown variable here, the reaction F in the y direction. So if we solve for that, we have the reaction of F in the y direction will equal, I'll try to fit it in here by writing small, 20 times 8 plus 10 times 16 plus 100 times 6, and all of that is going to be divided by 6 meters. So the reaction at F in the y direction will equal 153.3 kilonewtons. Now the reaction at E in the vertical direction, we can call this REY, can be found by summing the forces in the vertical direction. We have two externally applied 100 kilonewton loads, and we know that the reaction at F in the y direction is 153.3. So we could write this out and say the sum of forces in the y direction equals 0. That is going to equal negative 100 and another negative 100 plus 153.3 plus the reaction at E in the y direction. So the reaction at E in the y direction will equal 100 plus 100 minus 153.3. And that is equal to 46.7 kilonewtons. Now we also have a horizontal reaction at E, and it's the only reaction in the horizontal direction. Therefore, it has to resist all of the applied loads. So we have a 20 and 10 kilonewton lateral force being applied to this truss. So 20 plus 10 is 30, and so the reaction at E in the x direction is equal to 30 kilonewtons. So now that we know our reaction forces and our missing geometry, we can begin our truss analysis using the method of joints. So this is a kind of a big truss with quite a few joints. We've got 6 joints, and we can choose really any one of them to begin at. Sometimes it's best to kind of systematically work your way from one end of the truss to the other. And then sometimes it might be a good idea to pick out certain joints that might be a little easier to solve than others, sort of like picking the low-hanging fruit. For instance, this joint right here, F, doesn't have any diagonal members framing into it. We just have the vertical member DF and the horizontal member EF, and then we have the one reaction force. So this is an interesting joint to begin with. If we draw a free body diagram of it, we have the vertical reaction of 153.3. We have a vertical member and a horizontal member framing into it, and that is it. There are no other diagonal members framing into it. There are no other externally applied forces at this joint. So since this member is completely horizontal, it cannot provide a vertical reaction. Therefore, the entire 153.3 kilonewton force, that reaction force, has to be resisted by the member DF. So DF has to equal 153.3 kilonewtons, and it's pushing down against that joint, so it's in compression. So I can label that 153.3, and it is in compression, which means it's pushing down against joint F and pushing up against joint D. Now here's an interesting thing about this truss. If we look at this horizontal member EF, by investigating joint F here, there is no externally applied horizontal load. There is no internal horizontal load. There is no horizontal load at this joint. So therefore, the force in member EF is 0. This is what we call a zero force member. So it has 0 kips, so we can't really say it's in tension or in compression. It has no force in it at all. So you might be wondering, then what's the point of it? The point is to provide stability. It completes this triangle shape here. Without that triangle, there is no, this joint, this support, which is a roller, would not be stable. It would be free to move back and forth and could slide out to the side, and the whole truss would collapse. So although in theory it has 0 kips carried in it, in reality it probably does have a small amount of load in it from time to time, depending on how the external loads fluctuate. So it's there basically just to keep this joint in place. And although with the given load situation, it theoretically has no force in it, it is necessary to have this member to provide a stable truss. So I think this might be the first zero force member we've encountered in any of our truss analysis. So they do exist, and there is good reason for them, and it's important to identify them. So we've got a zero force member there, EF. So now that we're done with joint F, those are all 3 of the loads, and we found them all quite easily. Now it's time to move on to the next joint. So we could do that by going to either E or D. And I'm going to recommend that we go on to E, I believe. I think we'll have fewer unknowns at joint E. But I'm not going to have time to evaluate joint E in this video, so we'll continue the analysis of this truss in the next video by moving on to joint E.